Everyone, welcome to our next video for week 6. And today we're going to talk about the last of our week 6 hypothesis tests, the test for a single variance or a single standard deviation. In some cases, statisticians are interested in testing claims about the spread of data. For example, a company that produces medication will need to be certain that they are producing pills with dosages within a certain margin of error. So they want their spread, their standard deviation or variance, to be very small. Similar idea for companies that produce parts that are meant to fit together, like IKEA. You need the variation in those part sizes to be small so that the parts will fit together as intended. To test claims about the variation in a set of data, as measured by either the variance or standard deviation, we're going to use the same p-value method that we've used for other hypothesis tests. And this hypothesis test is going to work very similar to a test about a mean or a proportion. So let's take a look at how steps 1 and 2 change for a test about a single variance as opposed to a mean or proportion. So step 1, we're going to state the hypotheses. For claims about a variance or standard deviation, we follow the same rules as for means or proportions. The only thing that's going to change is the symbol that we use. So we use sigma squared if it's a test about a population variance, or we just use sigma if it's a claim about a population standard deviation. So your null hypothesis is going to be that statement of equality. So you're going to have your variance or standard deviation equal to the given population value. And then your alternative will be a statement of inequality. So less than, greater than, or not equal to. If you have a less than, it's a left tail test. Greater than is a right tail test. And not equal to is a two tail test, exactly like we saw for tests about a mean or a proportion. To calculate the p-value, we're going to have to do something a little different. First, we need to calculate that test statistic. Up to now, we've had a calculator function that will do that for us. For the chi-squared distribution, for the test of a single variance or standard deviation, there isn't a function on most calculators that will do this. So we're going to have to calculate the test statistic first, and then find the area in the tail on our own. This is a little different if you have a TI Inspire. I haven't heard anyone mention that they have one. If you do, send me an email and I can email you the directions for how to find the p-value on your Inspire, as it will look a little bit different. To calculate the test statistic, we're going to use the formula chi-squared equals n minus 1 times the sample variance divided by the population variance. So S squared is the sample variance. If you're given the sample standard deviation, you need to square it. If you're given the variance, it's already been squared and you don't need to square it again. Same for the denominator where we have our population variance. If they give you standard deviation, you need to evaluate that square. If they give you the variance, it's already been squared. Once you have your test statistic, you're going to calculate your p-value. And that really depends on what type of test you have. So we know that we can have 3 different tests. So we can have a less than test in our alternative statement. So that's going to be a left tail test. And remember that we're dealing with a chi-square distribution. So we're dealing with a skewed distribution. So a less than is going to look like this. This is going to be that test statistic. And then this area in that tail is going to be that p-value we're interested in. For a greater than problem, we're going to see the same idea, except now it's going to be the right tail. That boundary is that test statistic you just calculated, and the area in the tail is the p-value. And then we get to the not equal to test, and that's the one that's going to be a little weird with the normal distribution and the student t distribution. Those curves were symmetric about 0. So we could find one tail and we automatically knew what the other tail was because we knew that those test statistics were symmetric, same size, opposite sign. Here, if I have a two-tail, so area over here, the problem is that that test statistic is either here or here. So what you're going to do is you're going to assume that it's one of these cases. You're going to plug in the test statistic and you're going to treat it as a less than or a greater than. You're going to pick the value that's smaller and then double it, because what you would have just found is that p-value over 2. Half the p-values in the lower tail, half the p-values in the upper tail. So let's take a look at what that's going to look like on a calculator. So for the TI-84, you're going to use second vars. You're going to go into that distribution menu, and you're going to scroll down to option 8, which is chi-squared CDF. Don't use PDF, we want CDF. And what this is doing is it's going to take the test statistic that you put into it, and it's going to calculate the area under the curve, or the probability, which is our p-value. If it's a left tail test, so if it's this first case, your lower bound is 0 for that shaded area. You know, our curve starts at 0. And then the upper bound for that shaded area is the test statistic. If it's a right tail test, your lower bound is the test statistic. That's where the shadings start. And then the upper bound is all the way out at infinity. This curve keeps going and going forever to the right. And so we're going to use an upper bound of 1E99. If it's two-tail, again, you're going to try both of these. So treat that test statistic as if it's a left tail, as if it's a right tail, pick the smaller of the two answers and multiply it by 2. I'm going to clear these drawings so we can see the equivalent for the GeoGebra. GeoGebra is the same idea. You're going to have to do left tail, right tail, or two tail differently. The chi-squared function call on GeoGebra wants 2 pieces of information. It wants the degrees of freedom, n-1, and then the test statistic you calculated. If it is a left tail test, you're just going to call chi-squared degrees of freedom test statistic. If it's a right tail, you're going to do the complement, 1 minus chi-squared degrees of freedom test statistic. If it's two tail, you're going to try both and then pick the smaller and multiply by 2. We are going to do examples so you can see what this looks like in practice, and we'll do it both with the TI-84 and with GeoGebra. So let's jump into our first example. This is 1111 in your textbook. With individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoon is 7.2 minutes. The post office experiments with a single main waiting line and finds that a random sample of 25 customers, the waiting times for the customers have a standard deviation of 3.5 minutes. With a significance level of 5%, test the claim that a single line causes lower variation among waiting times, shorter waiting times for customers. So let's switch windows here so we can give ourselves some writing space. And let's go through and pick out everything that's given in the problem and what we're asked to do. So first, that question down at the bottom, test the claim that a single line causes lower variation. So I'm testing a claim about variance. It says variation, they're talking about variance. Or standard dev. So I know that I'm using this process we just talked about. The other thing is it says lower, that's a less than. And then let's pick through that problem. So first it says individual lines at various windows. PuffStuffus finds that standard deviation for normally distributed wait times is 7.2 minutes. So this right here is a population standard deviation. So we know that sigma, they're claiming, is 7.2 minutes. And then we're going to go to the next sentence. It says post office experiments with a single main waiting line, finds that for a random sample of 25 customers, so our sample size is 25. Sorry, my apartment complex is a little noisy. If you hear the background noise, I apologize. And then it says the waiting time for customers have a standard deviation of 3.5. That 3.5 minutes is attached to that random sample of 25. So that's a sample standard deviation of 3.5 minutes. And then they ask us to test this claim. When they talk about variation, both variance and standard deviation are measures of variation. Because they've given us standard deviation in both cases, we're going to assume that we're testing claims about standard deviation. So now that we know we're doing a hypothesis test for a standard deviation, we're going to set up our 4 steps. So our first is our hypotheses and our claim. The null is a statement of equality, and we see that right here. So our claim or assumption is that the population standard deviation for window wait time is 7.2 minutes. And then our alternative, we know it's going to be standard deviation 7.2. And we discovered in the statement of the problem that lower, so less than. And we're testing the claim that the single line causes lower variation. So this is the claim that we're testing. Based on our sample data, does that single line result in a standard deviation that's less than 7.2? Our second step, we're going to find our p-value, and we know that to do that, we first have to find our test statistic. And our test statistic is n minus 1 times s squared over sigma squared. So let's go ahead and plug those values in, see what we get. So we know that our sample size is 25. So 25 minus 1. We know that our standard deviation S is 3.5. And I need to square that. And then in the denominator, we know our population standard deviation sigma is 7.2, and we're going to need to square that. So I'm going to go ahead and grab, for this problem, my TI-84, and we're going to plug that information in. So I know 25 minus 1 is 24, 3.5 squared, and then divided by 7.2 squared. And we get 5.671, blah, 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 blah. I'm going to round that to 2 decimal places. So 5.67. you're absolutely free to round it out further, but you need at least 2 decimal places. Okay, so I'm going to come back over here and draw my curve. So I know I'm looking at chi-squared values. You know my chi-squared is skewed. And because this is a less than problem, this is a left tail. So my p-value is going to be over here. And that test statistic is right here forming that boundary, 5.67. So on the TI-84, I need chi-squared CDF. And then it's going to ask us for information. So let's take a look at what information it's asking us for. So second vars, option 8. And I hit enter. And it's asking lower bound, upper bound, degrees of freedom. So for a left tail, our lower bound is 0. Our upper bound is our test statistic. And our degrees of freedom is 25 minus 1, which is 24. Whoops. So running that function, we're going to get a p-val. Let's pull that calculator back up. And you can see I've already done this earlier today. So 0, 5.6724, paste, enter. And we get 4.20, blah, 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 e negative 5. So first I'm going to copy it as it appeared here. Sorry, 20, 20 e to the. And what this e negative 5 is, it's actually telling me my answer is 4.20 times 10 to the negative 5. It's scientific notation. And I know that negative 5 here is telling me move the decimal place 5 to the left. So let's go ahead and do that. 1, 2, 3, 4, 5. And that's going to result in 1, 2, 3, 4 zeros in front of that. So our p-val is 0.123442. For step 3, we take that and we compare it to our alpha, and we're told here our level of significance is 5%, so 0.05, and 0.00004 is much less than that. So we are going to reject our. For our summary, when we reject, we say there is enough evidence. And then we go back up to step 1, and our alternative is our claim. So we're talking about support. There is enough evidence to support the claim that. And then we go back to the word problem, and it says a single line causes lower variation among wait times for customers. So this section that is in parentheses in blue is the tail end to that summary. There is enough evidence to support the claim that a single line causes lower variation among wait times for customers. Okay, let's go ahead and move on to our next example. So this is an example out of another textbook, and it says a researcher knows from past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. A random sample of 24 cars is selected and inspected. The standard deviation is 12.5 minutes. At alpha equals 0.05, can it be concluded that the standard deviation is changed? Assume the variable is normally distributed. So let's go ahead and start by dissecting this word problem. So I see that towards the end, we have a question at alpha is 0.05. Can it be concluded that the standard deviation has changed? So can it be concluded? I know it's a hypothesis test. And then standard deviations change tells me it's a claim about a standard deviation. So I know I'm doing a hypothesis test for sigma. And we're going to go through, pick out the information. Researcher knows that the standard deviation is 16.8 minutes. So this information here is a population value. So we know that the population value is claimed to be 16.8 minutes. And then if we continue reading, random sample of 24 cars. So that's telling me that N is 24. And then is selected, the standard deviation is 12 minutes. Because that immediately follows the random sample statement, we know that that is our sample standard deviation. So our S is 12.5 minutes. And then they do give us that alpha value of 0.05. We now have enough information to go ahead and run that test. So for step 1, null and alternative, we know the null, sigma is claimed to be 16.8 minutes. For the alternative, we know it's a sigma and is 16.8 minutes. And then the symbol in between is coming from that word changed. Changed could be less than or greater than, so we're going to use a not equal to. And that is the claim we're being asked to test. Step 2, again, we need our test statistic before we can find our p-value. So n minus 1 s squared over sigma squared. Our n is 24, 24 minus 1. Our s is 12.5, and that's standard deviation. We do need to square it. And then on bottom, similar idea, the population standard deviation is 16.8. We need to square it. Now that we've got most of our information down, I'm going to minimize this really quick and rearrange our screen. Just a second here, if I can get this to cooperate, which seems to be questionable. We will pull GeoGebra up next to it so we can work with GeoGebra alongside our window. Maybe. Microsoft is always fun this way. Goodness, I'm having issues with tech today. Work. There we go. Scoot over our work and pull up GeoGebra. Thank you for your patience. Okay, so first we're just doing our plug and chug. 24 minus 1 is 23 times 12.5 squared divided by 16.8 squared. So we know our test statistic is 12.73. And then over here, I'm going to draw a quick picture. Chi-squared. We draw our right skewed curve, and it's a two-tailed test. So I'm going to draw both tails. And then this is going to be p-val over 2. This is going to be p-val over 2. And then I don't know whether my 12 is here or here. So I'm going to run two calculations and I'm looking for the smaller answer. So chi squared pops up directions that we cannot see. So hang on just a second. Degrees of freedom, and then our test statistic. Degrees of freedom and our test statistic. So we know our degrees of freedom is 23, and our test statistic is 12.73. And that's pretty small, but I'm going to check just to make sure. I'm going to do 1 minus pi squared, 23, 12.73, and we can see that 95 point something. So our p-value over 2 is the smaller of those numbers. So p-val is going to be 2 times that number, 0.4, oops, sorry, 0.4. 0.424. So 0.848. From here, we kind of already know what we're doing. Step 3, we compare that p-value we just found to the alpha. So our p-value is 0.0848, and our alpha is 0.05. 0.8 is bigger than 0.5. So p-value is bigger, we're not going to reject. Do not reject the null. For step 4, since we did not reject, there is not enough evidence. And then looking back at step 1, our alternative is the claim. So we're talking about support. There is not enough evidence to support the claim that. And then again, we go back to that word problem to look for the phrasing. And it says, can it be concluded that the standard deviation has changed? So there is not enough evidence to support the claim that the standard deviation of the time it takes to inspect a car has changed. Okay, I'm hoping that that didn't feel too scary. If it did, you can send me an email, a text message, or drop by office hours Tuesday, Thursday, or Saturday. I hope you have a great rest of your week, and I'll see you in our next video.